Okay, so I finished this off for us, and sorry, I made a mistake earlier. 4 should not be part of our table because it says at least 4 are red. So 0, 1, 2, or 3 would be the complement. 4 would actually be part of the set we're looking for, not the complement. So if we look at the probability of getting 0 red candies, it's very low. Probability of getting 1 is also quite low. 2 is fairly low. 3 is starting to get higher, right? So, if we add all these things up, we arrive at 22.5%. And if we subtract that away from 1, we arrive at 77.5%, which is going to be our answer to the problem, right? The probability that at least 4 candies in a given box are red is 77.5%. Okay, and that comes from our calculations here, all the different cases that we could do, and we added them all up because that's what we do with OR. Okay, Mary purchases a box of candies and is disappointed to find 6 red Smarties because they are her favorite. Should she be disappointed? Well, we can answer this question easily if we use our expected value formula. And the expected value for the number of Smarties in a box would be 20 in a box times the probability that it's red, which is 0.5, which actually is only 5. So she is being unreasonable here, probably understandable given the age of this person. To expect 6, right? 6 is actually higher than the expected value. So since the expected number of red Smarties in a box is 5, Mary should count herself. No, let's just say Mary should not be upset to get 6, which is actually higher than expected. Okay, if we wanted to give more detail on this question, we could go ahead and calculate the probability that that she ends up with more than 6, which I mean let's just do it using the computer here. So here's 6. The probability that x is greater than or equal to 6 is, about 38%. So, 1 out of 3 times she might get more than 6 Smarties, but in general, she really shouldn't expect that, right? She really shouldn't expect to get more than 6. Okay, an 8-sided die is rolled 12 times. What is the probability of rolling a 7 at least twice in those 12 rolls? Okay. Let's finish this off today. This is the last thing we are to do. So we have x, we have p of x, and then we're going to add them up. And at least twice means we need 0, we need 1, we need 2. All right, here's x. Here's p, that capital X is equal to lowercase x. An 8-sided die could be rolled 0 times. We could get 7 0 times. We could get 7 once. We could get 7 twice. P is 1 out of 8 because there's 1 out of 8 ways to roll a 7 with an 8-sided die. Q is 7 out of 8. It's the other 7 ways you can do this. N is 12 times, and finally X is equal to 0, 1, 2, and 3. We're going to calculate them one at a time. Okay, so again, this is nothing new here. I mean, this is all the same thing that we've been doing. So we'll just, let's go through this one and just get the numbers for it quickly so you have them in your work. So again, N is 12, P is 1 out of 8, Q is 7 out of 8, S is, let's start with 0. So 0 successes, we get 20%, right? 12 choose 0, 1, 2, 5, 0, 8, 7, 5, 12. Right, so we get 0.2014. Okay, for 1 success, right, we use the exact same formula as before. We just change this to a 1, put that as a 1, and drop that down to an 11, and we arrive at 34.53. And then we will let's try 2 7s. which is 27.13%. So all of these are fairly likely, right? And this should make sense to us because if you roll 3 or 4 or 5 or 6 all the way up to 12 sevens, they're not going to be that likely. Like most of the time, we should expect to find 0, 1, or 2 sevens in our set. Again, a quick demonstration of this. Let's set P equal to 1/8. Let's set N equal to 12. And A, we're looking for our number of successes here. You can see, if we look at our histogram here, a lot of zeros, a fair number of ones, a lot of twos, not too many threes, very few fours, and virtually no 5, 6, 7, 8, 9, 10, or 11th, right? No, it doesn't make sense. You're going to roll 11 times in a row on an 8-sided die. It's quite likely we'll get 0, 1, or 2. We might get 3 or 4, and anything beyond 5 is really quite uncommon. Okay, if we were to add up all of these things, right? Remember our final statement here, P that X is, why is this underlined? X is less than or equal to 2 is given by P of 0 plus P of 1 plus P of 2, right? And then just to be formal, let's write X equals in each of these things. And X equals, no, capital X. Okay, so we're going to add all these things up, and we arrive at the conclusion that, okay, so sorry, A should be 2, and we want X is less than or equal to A. We arrive at an 81.8% chance, which when we add these things up is what they should create. Okay, so this has been the lesson on the binomial distribution. You are to use this distribution when you have met these two conditions. If you can define the event as success or failure, P and Q, everything that is not a success is a failure. Everything that is not a failure is a success. If we have more than these two options, this formula does not work. This formula also only works when the trials must be independent. Okay, if they are not independent, this does not work. Dependent, English teacher. Okay, trials must be independent, otherwise this formula does not work. If throwing one die affects the next die, you cannot use this. Lastly, our expected value is given by N times P, which is great for us because otherwise we would have to make this table. We'd have to multiply X times P of X every single time and then add them all up, which is an insane amount of work. So we luckily have this little formula here at the end. E of X is equal to NP, which again is highlight that, please circle it and make sure you use it. It saves a ton of time. Take a few minutes to look through the learning goals and the assessments, self-assessments here. If you have a question about this one, you can send it to me on D2L, or remember we have all of Monday to go over any questions that you have. Enjoy the rest of your day.